All right, so we've talked now a little bit, like I said, about Le Chatelier's principle. What happens when we kind of change the system a little bit? If we change the system by adding or removing one of our reactants or products, right, then we can use Q to kind of understand and explain which direction our reaction will proceed. Again, we use run from the fat guy, fill the hole just in our mind, okay? So now, though, let's think about some other changes that could occur. What if we had a piston, right? If we had a piston, we are going to compress and increase the pressure of our system. So if we increase the pressure of the system, that will also change our equilibrium concentrations, okay? So if we think here, right, we have one molecule on this side and two molecules on this side. Those two molecules are both gases where we only have one gas molecule on the left. Again, anytime we have gas molecules, right, at relatively ideal conditions, they're going to take up more space, okay? So essentially what we can say is, right, same idea is that if our pressure changes, we can then change our reaction system as well, okay? So if we increase the pressure, then we want to get rid of moles of gas. So our reaction is going to go towards fewer moles of gas. Okay, so if we decrease the pressure, now we're going to be able to produce more of our NO2, right? We're going to be able to produce more of the NO2 because our N2O4, right, where it's different pressures. This does not change our K value, right? Whenever we add or remove one of our reactants or products, or if we change the pressure, this does not change the K value. All it's going to do is it allows for more molecules to be around or wants fewer molecules around. Okay, so this has to do with our gases, right? The last thing that we can say is that what about heat? What if we increase the temperature or decrease the temperature? That is going to affect our K value, but it is also going to be kind of the same idea where we need to run from the fat guy or fill the hole, okay? So here now, right, if this is our reaction, we can actually rewrite it as N2O4. We've got plus 57.2 kilojoules. We're going to put that on the left side because we need to add 57.2 kilojoules of heat in this system, right? We've got our equilibrium forming 2 NO2. So now if we increase the temperature, right, we increase the temperature, this goes up, we've got a fat guy, we need to run from the fat guy, we are going to move towards the right, right? This depends on whether our reaction is endothermic or exothermic, okay? So depending on the value of our enthalpy, right, we would either put our enthalpy on the left or the right, and that tells us those energies. So that will tell us about how our reaction will move away from or towards the heat, okay? So when you heat this up, right, it has more energy, so more energy, it will want to move towards the products here. But if it were exothermic and we heat it up, it's actually going to want to go the other way to, again, use up some of that extra energy that is around, okay? So this is all about being able to place our enthalpy in the right spot, and then we can still use that same expression as we have before, okay? This does change our K value, okay? Heat does, whoops, change. Wow, I had a hard time spelling there. Heat does change the K value, okay? All right, so we've got one last topic to talk about, and that has to do with solubility, okay? So our solubility is really kind of an application of our equilibrium, okay? So solubility, right, we've talked about solubility just a little bit. Let's remind ourselves we've got 4 ions that we say are always soluble, right? If we've got nitrate, NO3 1 minus, if we've got sodium, Na plus, potassium, K plus, or NH4 plus, ammonium, those ions are always going to be soluble in water, okay? So they are soluble because their K value is very, 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 very large, okay? It's much greater than 1. So because of that, we are always going to go towards dissolving them, okay? So if we write the dissolving reaction, right, the dissolving reaction, maybe the solvation, right? The solvation expression here, we start from our solid, and we go towards our separated aqueous ions. Again, right, if we were to write the K expression, the solid is not going to show up in that expression. But we can still write the K expression here. So in this case, K equals concentration of Ag plus times the concentration of Cl minus. Okay, so our K value here is going to be much smaller than 1. Turns out for silver chloride, it's much smaller than 1. The K value, KSP, solubility product, KSP, solubility, right? KSP is 1.8 times 10 to the minus 10th. So that is what it equals, okay? So what we can do with this, right, calculate the solubility of silver chloride in 5 liters, we can calculate how much silver chloride will dissolve in 5 liters, right? This is a pretty big gallon. So we can say, okay, right, our KSP, 1.8 times 10 to the minus 10th equals our concentration of Ag plus times the concentration of Cl minus, right? Really, this is going to be equal to x times x, right? So that would be x squared. So let's take and solve for x here. X is going to equal the square root of 1.8 times 10 to the minus 10th. So I'm going to put that in here. And that is equal to 1.3 times 10 to the minus 1, 2, 3, 4, 5. That's what I thought. Okay? So that is going to be our concentration for silver plus, right? Ag plus. So that's our concentration. That's a molarity. Well, how many moles are going to fit in 5 liters, right? If we write this instead as a moles per liter, we can say, okay, well, we can multiply that by our 5 liters. Our units are going to cancel. We are going to get 6.7 times 10 to the minus 5th moles of AgCl to dissolve in 5 liters. Very, very small, right? Silver chloride is really not a very soluble ionic compound, okay? So we're going to pause and we're going to come back in just 1 second here.